So we know when and why we should transform variables in machine learning. Let's now go over the main mathematical functions that are normally used together with these statistical methods. Throughout the years, a lot of mathematical transformations have been used and studied together with the use of statistical models. These are the logarithmic transformation, the reciprocal transformation, the square root, the arcsin, the power transformation in general, and then two transformations that automate the evaluation of many transformations, which are the Vox-Cox and the Io-Johnson. In this video, we're going to talk about the mathematical transformations specifically, and then in later videos we will discuss the Vox-Cox and the Io-Johnson. So let's get started. You're probably familiar with the logarithmic transformation. We just transform the original variable by applying the logarithm. So the transformed variable is the logarithm of the original variable. The logarithm is very good at dealing with positive data with the right skewed distribution. These are distributions where the observations accumulate at lower values of the variable. A good example of this variable is the median income variable that we obtain in the Californian housing dataset that we find with scikit-learn. You can see that this is positive data with a right skew, and when we transform this variable utilizing the logarithm, we obtain a more Gaussian-looking form of the distribution. So logarithm transformations are suitable when we see these types of distributions in our variables. Now the logarithm is of course restricted to positive variables. The reciprocal transformation is useful when we have ratios, that is, values resulting from the division of two variables. And classical examples of this variable are population density, which is created by dividing the number of people in a certain area, or as we will see in our example, house occupancy, which is the number of people within a house. And the reciprocal transformation is given by 1 over the original variable. In this example, I use the average occupancy from the California housing dataset, also from scikit-learn, which we can see is a very skewed distribution. And when we apply the reciprocal transformation, this is 1 over the original variable, we see that now we have a better spread of the values over a wider value range. The square root transformation is usually singled out as a mathematical transformation because it is suitable for variables with a Poisson distribution, and variables that usually follow a Poisson distribution are those that are counts, for example, number of children, number of pets. The square root transformation tends to transform variables that are counts into a new variable with an approximately standard Gaussian distribution. The square root transformation is a form of power transformation where the exponent or the power is 1 over 2 or 0.5, and it's only defined for positive values. So here we see a representation of the square root transformation where we just take the square root of x, or equivalently, we power x to 1/2. For this demo, I created a toy variable that follows a Poisson distribution, and then I applied the square root transformation. In a histogram, it's very hard to see the change, but we can see the change that the transformation caused on the variable if we create a QQ plot. Here we can see that the variable doesn't follow the red line, but after the transformation, the counts are more aligned over the red line. So this is a more, if you want, Gaussian-looking transformation of this count-based variable. A transformation that you may not have heard of is the arcsin transformation. This is rarely used in machine learning, but it was described as one of the mathematical transformations that can be used to help meet the assumptions of statistical models back in the day, so I will describe it to you just so you know that it exists. The arcsin square root transformation is good at dealing with probabilities, percentages, and proportions, so these types of variables, and the values of the variable that is going to be transformed should vary between 0 and 1. And it's given by the arcsin of the square root of the variable. And here I applied the arcsin transformation to several variables of the breast cancer dataset from scikit-learn, which vary between 0 and 1. And we can see that in many of them, this arcsin transformation does improve the value spread, like for example in the variables at the top and also in the variables in the second line. So know that it exists, and if you want to apply this transformation, you can do it very easily with the libraries that we're going to describe later on in this section. The power transformation consists in transforming the variable by powering the values of the variable to a certain exponent. And this exponent needs, of course, to be optimized. It could be part of some hyperparameter optimization. And as a general guidance, if the data is right skewed, so if the observations accumulate at the lower values of the variable, we would use lambdas smaller than 1. But if the data is left skewed, this means if the observations accumulate around higher values of the variable, we would normally use lambdas greater than 1. So in practice, we normally don't do power transformations because, as we will see in the next video, the Vox-Cox transformation automates the search of the lambda for us. So let's move on to the Vox-Cox transformation.